Good morning, students. Today we will discuss one topic, eddy current. We have finished almost all the topics of chapter 6, only this topic was left. So today we will do that and we will discuss numericals based on other topics also. Eddy currents. Currents can be induced not only in conducting coils, as we have seen in almost all topic of this chapter, starting from Faraday's law of electromagnetic induction, that there is induced current produced in a coil whenever there is change in magnetic flux. So this current can be induced not only in the conducting coil but also in conducting sheets or blocks of metals. If they are of conducting material, some block, some sheet is there is also induced current. And this induced current is in the form of closed loop. This induced current flow in closed paths in planes perpendicular to the lines of force throughout the body of the metal. These currents look like eddies because they are closed paths and perpendicular to the magnetic field lines. So they are called eddy current. Their direction is given by Lentz's law because they are due to induced current. They are just induced current but in the form of closed path, because here conducting coil is not a coil, it is a block. So block is considered to be made up of different settings. So there are induced current produced in closed paths. They give rise to eddy currents. So there is some undesirable effect of eddy current. Eddy currents are produced inside the iron cores of rotating armature of electric motors and dynamos. Now just imagine the construction of generator or motor. You all have studied in 10th class. What happens there? There is a coil which rotates in between the pole pieces of magnet, which rotates. Then because this coil is of metal and it is rotating in between magnetic pole pieces, so magnetic flux is changing every time. So magnetic flux is changing means induced current is producing again and again. So eddy currents are produced inside the iron cores of rotating armature of electric motors and dynamos, and they cause heating. There is heating effect of current. Either it is induced current, either it is any type of current. Current always give rise to heating effect because of resistance of the metal in which it is going to be passed. So this heating leads to wastage of power, which may damage the insulation of coils. So this is undesirable effects of eddy current. But there is some desirable effect also, and to minimize the undesirable effect, eddy currents can be reduced using laminated core instead of single solid mass. When it is single solid mass, then eddy current will be like this. Now if it is, this block is not solid, it is cut into very thin pieces, thin slices, and that also laminated and then also joined. So this closed path will be shortened. That is why eddy current can be reduced. So when eddy current is less, heat produced will be less, so wastage of power will be less. In this way, eddy current can be minimized. Now there are some applications also of eddy current. Number 1, in induction furnace. As we discussed in this point, that whenever current is passed, this current can produce heat. So heat, if large amount of heat is produced in a metal piece, then it can be used, this surface can be used for heating something. So induction furnace is based on that principle. If a metal specimen is placed in rapidly changing magnetic field, then very large eddy current is set up and they are sufficient to even melt the metal. Number 2, electromagnetic damping. When a current is passed through a galvanometer, electromagnetic damping. When a current is passed through a galvanometer, its coil oscillates before coming to rest in the final position. You all have seen that when we use galvanometer in the laboratory, its needle deflects very fast, and then it should come to rest when there is no current. As coil moves in magnetic field, in the construction of moving coil galvanometer, if you remember, we have done this article in chapter number 4, that as coil moves in magnetic field, then there is torque, and this torque is proportional to current. At that time, we discussed only current and torque. Now, at the same time, when current is there, magnetic field is there, and this is deflecting, which metal is deflecting, so it means induced current will be present there. Due to induced current, eddy current will be present there, so that will stop the deflection. So, induced current is set up in the coil which opposes its motion. The oscillations of the coils are damped. Damped means it is less in amplitude, it comes to rest. This is called electromagnetic damping. This damping can be further increased by winding the coil on a light copper or aluminium frame. As the frame moves in magnetic field, eddy currents are set up in the frame which resist the motion of the coil. This is how a galvanometer is made deadbeat. This is how a galvanometer is rendered deadbeat. That is, the coil does not oscillate, it deflects and stays in final position immediately. So it depends upon the need whether we want to reduce eddy current or whether we want to make it utilization. So in electric brakes also, because it is in opposite direction, so it can be used in brake also. A strong magnetic field is applied to a rotating drum attached to a wheel. Eddy currents set up in the drum exert a torque in the drum so as to stop the train. So when current can produce this type of motion, then induced current also can produce anti-clockwise motion. So it can be used as brake also. Electromagnetic shielding. When a magnetic field is electromagnetic shielding. When a magnetic field is suddenly switched on, large eddy currents are produced in the sheet. The change in the B is only partially detected at P. On the other side of the higher is the conductivity, better will be the shielding because of this induced current, eddy currents. So magnetic field, because this is field, and here conducting sheet. In conducting sheet there are induced currents. So P point is devoid of magnetic field. So this is called electromagnetic shielding. So eddy currents, this is very important topic. Sometime it is asked about its applications and its uses also. Numerical problems. We will discuss two numerical, one based on self-induction and one based on mutual induction. And they are from NCERT textbook. They are very important to understand that self-induction depends upon number of turns. It depends upon area and it depends upon permeability of the medium. An air-cooled solenoid, here air-cooled solenoid with length 30 cm, area of cross section 25 and number of turns 500, carries a current of 2.5 ampere. Current is suddenly switched off in a brief time of 10 to the power minus 3 second. How much is the average back EMF induced across the ends of the open switch in the circuit? So we want to find back EMF, means E. E is equal to LDI by dt. So first we are required to find L, because di by dt we know. We are required to find L. So to find L, let us take this length of the coil is 30 centimeter. First we will write the given quantities. Then we will change the given quantities in proper SI unit. So length is 30 centimeter. This is 0.3 meter. Area is 25 centimeter square. Centimeter square means we will multiply it by 4, converting into meter, 10 to the power minus 2 square. So that is why 10 to the power minus 4. Number of turns 500. Rate of change of current di by dt means final current minus initial current upon, this is initial, this is final. So change can be, this is magnitude of change. If we want change is always from final to initial. Current is switched off, it means final current is 0. So change is always final minus initial. So 0 minus 2.10 to the power minus 3. This is time mentioned here. But current is decreasing. So current is decreasing. So back EMF will be there because current is decreasing. It means flux is changing. Flux is changing means induced EMF will be there. So E is equal to LDI by dt minus LDI by dt. So L is self inductance for a long solenoid, and L is equal to mu naught N square A L. Yesterday in previous class we discussed this formula, self inductance for a long solenoid as well as mutual inductance for a long solenoid. So L is equal to mu naught N square A L, where N is number of turns per unit length. Now substitute the values. E will be minus LDI by dt. So L is this one, di by dt this one. Now di by dt is also negative. So this negative and this negative will become positive. Di by dt is also negative. This minus become positive. Finally becomes positive. So substitute the value. Mu naught 4 pi into 10 to the power minus 7. Number of N will be taken as N upon L. N is 500. L is 0.3. So point N square means N square upon L square. So 500 into 500 upon 0.3 into 0.3. Area. This is area 25. This is area. L is 0.3. And di by dt is minus 2.5 into 10 to the power minus 3. This minus will be cancelled by this one. Now if we solve this, we will get 6.542 volt. When this induced EMF is 6.542 volt, if we want to find the direction, then we will draw a solenoid. This is our solenoid. In this case, our current is decreasing. Current is decreasing. So let current is from this side. Our current is decreasing. When current is decreasing, induced current should support it. It should support. So induced current will be also in the direction. So it means this end is positive and this end is negative. Where arrow is going, this is positive and this is negative. So direction of induced current can be found using Lenge's law. In this case, Vp minus Vq is equal to minus 6.542 volt and Vq minus Vp is 6.542 volt. This point is very important. Generally, this type of questions are asked in examination. What is the EMF between this point? So you must understand how we find EMF. Now, numerical number 2. It is based on mutual induction. A toroidal solenoid with an air core has an average radius of 15 centimeter and area 12 centimeter square and 1200 tons. Obtain L. First we will find L. It is mixture of because in mutual induction there are two coils. So naturally if we know L we can find also M also. So obtain L. This is first part. Second part, a second coil of 300 tons is wound closely on the toroid above. Now it is toroid. If the current in the primary is increased from 0 to 2 in this second, obtain the induced EMF in the second coil. Now it is not a solenoid, it is toroid. The uniform magnetic field set up inside a solenoid is this. We can say solenoid also and toroid also. Formula is same. So B is equal to mu naught Ni. Mu naught Ni. N means number of turns per unit length. But in case of toroid, number of turns is N and length is 2 pi r. For toroid, length is 2 pi r. So total flux will be B dot A. Total flux will be B dot A. And total flux linked with N turns will be, because here turns are involved. Generally when we discuss in topic, we take 1 turn. But when in numericals, we need number of turns. So we should multiply it by the formula. So phi is equal to BA is for single turn. Phi is equal to NBA is for number of turns N. So put the value of mu. We will write mu naught N square. We will get L is equal to mu naught N square A upon L. But here L will be 2 pi r. L will be 2 pi r. Because phi is equal to Li. So leave this I, other will be L in this formula. Phi is equal to this one. Leave the I. Take I this side. Other factor, remaining other quantities will be L. So L is equal to mu naught N square A upon 2 pi r. In case of solenoid, it was mu naught N square A upon L. We can find value of L because everything is given to us. This is mu naught. This is number of turns. This is area of the coil. And this is 2 pi. And this is radius of the coil. 2 pi r. This is radius. So answer is 2.3 into 10 to the power minus 3 Henry. Unit of L is Henry. If you don't write Henry, half marks will be deducted. Part B. Now N1 is 1200 because this is primary, on over which secondary is there. N2 is 300. dt is 0.05 second. di is increased from 0 to this. So final is 2. Initial is 0. So increase is 2a. The EMF induced in the second coil is E is equal to mdi by dt. M is, formula of M is mu naught. In this we can remember from there. Mu naught, mu naught. Here N square will be split it into N1 into N2. Rest will be same. Rest will be same. This N square is split it into N1 into N2. Area will be same. Length will be same. 2 pi r. So 2 pi r is the primary. 2 pi r is of primary. And this area is of taken, that is also of primary. So 1200. Mu naught 1200 into 300 into area. This is area. Area is 12 centimeter square. 12 centimeter square. So this area is changed. This is E minus mdi by dt. M is this one. Put the value of M, mu naught N1 N2 A upon L into di by dt. So we will write L is equal to 2 pi r. This is 2 pi r. R is radius. So this is di by dt. So write area also. Area is we will take area 12 centimeter square. 12 into 10 to the power minus 4. So after multiplying all these values, we will get, after multiplying all these values, we will get 0.023 volt. We should take area also. Its value is 12 into 10 to the power minus 4. So we will get value E is equal to 0.023 volt. So practice other numericals also. But generally the type of numericals asked in board examination we have covered in these videos. First type of numerical is to find direction of induced current in case of magnet, in case of solenoid, in case of current carrying wire, and second is self induction, third is mutual induction, then fourth is motional EMF. Numericals can be asked from Faraday's law of electromagnetic induction also to find calculate induced EMF. So you have to practice all these types of question. Our chapter 6 is finished now. From tomorrow we will start chapter number 7.